So we're here at the example table, and in this video we're going to find the area under the curve f of x equals x squared minus x from 0 to 5. So let's just remind ourselves about what this means. The notation, in general, if you want to find the area under a curve f of x between a and b, then we take the integral from a to b of f of x dx, right? This is the notation. And by definition, this is the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I delta x. Now what is x sub I and delta x? Well, where delta x is b minus a over n, and x sub I is I times delta x. We want to start at a, so we need to shift by a. So remember, the basic idea behind this is we're putting a bunch of rectangles under the curve, and the width of each rectangle is delta x. The height is given by this f. We add up all those areas using this sum. And to make that approximation ever better, we make delta x smaller and smaller, which is done by making n larger and larger. So the idea is when we take the limit, we'll get the exact area. Now here, a is 0 and b is 5, right? So our delta x is 5 minus 0 over n, so 5 over n. And x sub I is I times 5 over n plus a, which is 0. So we get 5i over n plus 0, or simply 5i over n. So I want to figure out what this summation is first. I'll figure out what that is, I'll simplify it, and then I'll worry about the limit. So instead of having to write the limit each time. So let's figure out what this is and simplify. So we've got the sum from I equals 1 to n of f of x sub I. Now x sub I is 5i over n, and remember our function is x squared minus x. So we take 5i over n and we square it, and then we subtract x, which is 5i over n. All right, this is f of x sub I. And we multiply this thing by delta x, which is 5 over n. All right, so let's use some summation rules to simplify this. We can factor this 5 over n outside, and then we can split the summation into two summations because we have something minus something else. So we get 5 over n times the summation of this first thing, 5i over n squared. So summation from I equals 1 to n of 5i over n quantity squared. And then we'll subtract this one. So minus 5 over n. Remember, we factored this 5 over n out at the beginning. So each of these two things will end up with a 5 over n on the outside. So 5 over n times the sum from I equals 1 to n of 5i over n. Well, now what can we do? Anything that doesn't involve an I in it can be pulled out in front of the summation sign. So the only thing that has an I in it is right here. It's this I. We have a 5 squared. No I in it, so we can factor out a 5 squared. We then divide by an n squared, and we can factor that out. There's no I in the n squared. So when we factor out this 5 squared, we get 5 times 5 squared, which gives us 5 cubed, or 125. When we factor out the n squared from the bottom, we multiply that by the n outside, and we get n cubed. Now, what are we left with inside? Sum from I equals 1 to n. All we have is I squared. Let's do something very similar. Oh, this should be a minus. Let's do something very similar with this. This 5 doesn't have an I in it. We can pull it out. This n doesn't have an I in it, and we can pull it out. Think of these things as corresponding to the rules that say you can factor a constant out when you're differentiating. Right? If you have c times f of x, you factor that c out and differentiate f of x. It's the same kind of thing going on here. So when we pull this 5 out, we get 25, 5 times 5. And when we pull this n out, we get an n squared. So 25 over n squared times the sum from I equals 1 to n of I. Now we have these nice formulas that tell us how to write the sum from I equals 1 to n of I squared without a summation. We have another one that tells us how to do it when it's just I. So this is 125 over n cubed times the formula. We'll use the formula now that says this summation is equal to n times n plus 1 times 2n plus 1 all over 6. Now, minus 25 over n squared times, now we'll substitute the formula for the sum of the I equals 1 to n of I. This is n times n plus 1 over 2. Now we can simplify a few things. So we have an n over n cubed. So this goes away. This 3 becomes a 2. And we have an n over n squared. So this n goes away and the squared goes away. We're left with just an n in the denominator. We can also factor out some common stuff. The 125 and 25, the constants, these share a factor of 25. So let's factor out 25. Both of these terms also have an n plus 1 in them. So let's pull out an n plus 1. And what about in the denominator? We have an n squared here and we have an n here. So we can factor a single n like this. Then what are we left with inside? This 125, we pulled out a 25. We're left with 5. We pulled out an n plus 1, so we're left with this 2n plus 1. And then we divide by 6. We only pulled out one of these two n's here. We had n squared, we pulled one of them out, so we're left with 1 inside. So we have 6n here. Minus what? Well, we pulled out a 25, we pulled out the n, we pulled out the n plus 1. This n was already canceled, so all we're left with, this numerator becomes a 1, and we're left with a 2 in the denominator. So we're left with minus 1/2. So I'm now very glad that I did this before writing this limit down, because otherwise I'd have these limits at each step. So now I know how to write the summation that's in question without a summation. So now let's figure out the area under the curve. So the area under the curve, the integral from 0 to 5 of x squared minus x dx. Right? This is the notation we use for area. This is, by definition, the limit as n goes to infinity of the sum from I equals 1 to n of that thing we had before, 5i over n quantity squared minus 5i over n times 5 over n. Right? This is f of x sub I, and this is delta x. But all that work we did was to show how to write this summation without a summation. So this is the limit as n goes to infinity of 25 n plus 1 over n times 5 times 2n plus 1 over 6n minus 1/2. Now we can look at what happens to each piece of this. As n goes to infinity, here we have n plus 1 over n. Thinking of these as polynomials, they have the same degree. So we know that the limit of this ratio is just the ratio of the leading coefficients. Well, the leading coefficient in the top is 25, because if we multiply this out, we get 25n plus 25. We have a coefficient of 1 in the denominator, so this first part goes to 25. What about this second part, the part in the brackets? We have another ratio here of polynomials, same degree, right? Degree 1, degree 1. So we look at the ratio of the leading coefficients. The leading coefficient on the top is 10. The leading coefficient on the bottom is 6. So that goes to 10 over 6. And then we subtract the 1/2. So this is equal to 25 times, this simplifies to 7 over 6. And if we want, we can multiply this out, and we get 175 over 6. Oh, of course, this should be a 5.